Today we are going to learn about waves. A mechanical wave is a disturbance in matter that carries energy from one place to another. It's not a light wave. A light wave doesn't actually need any matter to carry it anywhere. It can go through outer space. But a mechanical wave must have a solid, a liquid, or a gas that it can pass through. The material through which the wave travels is called a medium. For example, the sound waves from my voice are traveling through the medium of the air. A mechanical wave is created when a source of energy causes a vibration to travel through a medium. Like we said, it's not light electromagnetic waves. Those don't have vibration and they don't need a medium to travel through. Here's an example of a medium, this rope. See the tag right there? See how the wave travels through the medium? But notice, the orange tag just goes up and straight down. It doesn't actually move along the wave, so the matter just shakes in place up and down and does not actually travel along with the energy. That is an example of a transverse wave. A transverse wave simply makes this shape, and the motion is up and down, which is perpendicular to the direction in which the wave travels. So the energy of the wave was traveling sideways, but the actual matter in the wave was traveling up and down. In order to have a transverse wave, the medium through which it travels must be a solid. In this picture of a transverse wave, we have labeled the crest and the trough. The crest of the wave is the top of the wave. The trough is the bottom. For example, animals will drink out of a watering trough, and if it wasn't curved this way, the water would spill out. The wavelength is the length of one wave. It's the distance between two crests or two troughs. If you measure from the origin of the wave or the middle, you have to be really careful, because to get a full wavelength, you have to go from the middle to the bottom, back to the middle. That's not a full wavelength, that's a half a wavelength. To the top and back to the middle. So from here to here is one wavelength if you start at the origin. That's why the definition says from crest to crest or from trough to trough, because that's a lot easier. An example of a transverse wave, once again, is a wave through a rope, through a blanket, and some earthquake waves are transverse waves. Next, we have longitudinal waves or compressional waves. Sound waves are an example of these. When I speak, it shakes the air as it goes to your ear. This is kind of like a slinky. You can see the compression travel along the slinky when I shake it. That is a compression, and one of the stretched out places is called a rarefaction, because it is rarer to find the wave in that location. It's spread out, and then the wave is compressed in the compression. The amplitude is determined by how far each little piece shakes before it returns to its place. The amplitude of a transverse wave is the height of the wave, starting from the origin to either the top of a crest or from the origin to the bottom of a trough. The motion in a longitudinal or compressional wave is back and forth. The energy travels sideways and the motion is sideways. Finally, surface waves are where two different mediums come together. For example, water and air. The particles within the medium actually travel in circles near the surface of the medium. An example would be ocean waves and some earthquake waves. Let's take a closer look at some of these types of waves. First of all, a transverse wave. You'll notice, if you'll watch one of these little dots, they simply move up and down in place. They don't move side to side, they just move up and down. The energy, however, does move from side to side. That's a transverse wave. Now let's take a look at a longitudinal wave or a compressional wave. Both of these pictures show a longitudinal wave. If you'll notice, if you'll follow one little dot with your eyes, it just shakes back and forth. It always comes back to where it started. The energy, however, continues to move across the screen. If you'll notice in the bottom picture, they have drawn an arrow to help you keep track of one of the dots. They have also shown the motion of the energy, shown by the black arrow with the word wave, and the motion of the individual particles, shown by the red arrow. Here is a surface wave. Follow the yellow dot with your eyes. Isn't that cool? It's going in a circle. That's the difference between a surface wave and a transverse wave. They look similar when you draw them on paper, so you actually have to see the motion of the individual particles to understand what's going on. Ocean waves do this. If you're swimming in the ocean and you're out past the place where the waves are breaking, you'll notice that the waves will simply pick you up and let you down over and over in a sort of circular motion. The waves only crash when they get close to the shore because the depth of the water has decreased so much. So as we have said, a mechanical wave is a disturbance in a medium or in matter. The medium or the matter does not go anywhere. The energy is what moves. The matter simply shakes back and forth in place, or up and down, or in a circle in place. The amplitude of a wave is the wave height, or the wave shake if it's a longitudinal wave. This tells how much energy the wave has. If light has a higher amplitude, then it's brighter. If light has a smaller amplitude, it's dimmer. If sound has a larger amplitude, it's louder. If sound has a smaller amplitude, it's quieter. The wavelength is the distance between two crests or two troughs, or for a compressional wave, it's the distance between two compressions or two rarefactions. The wavelength is the length of one full wave cycle in meters. The frequency of a wave is how often a wave comes past. It is how many wave cycles will pass by per second. The unit is one understood wave cycle per second. So the unit is 1 over seconds, which is the same thing as seconds to the negative 1. And a wave per second is a hertz. We hope that doesn't hurt your brain to think about. But you may have heard of this before when you tune your radio to 94.1 megahertz. That's actually the frequency of those radio waves. Next, the velocity of a wave is the speed of a wave. It's how fast the wave energy is traveling. The velocity of a wave is measured in meters per second. And by the way, the amplitude of a wave is independent of the wavelength, frequency, and velocity. It is not actually affected by any of those. There is a formula on your reference table when you're calculating the velocity of waves. It is the velocity of the wave, or wave velocity, is equal to frequency times, what is that? It's the Greek letter lambda. And I guess they'd used W for something else, like work, so they decided that Greek letter lambda is going to stand for wavelength. Don't worry, if you forget, you're going to have a reference table on your test. I like to write this formula without using the subscript of W because it tends to get me confused. I try to fill in the wavelength and the velocity here, but I shouldn't. It should be velocity, frequency, wavelength. In fact, if you'd like, you may rewrite this formula, velocity equals frequency times wavelength, using letters that make more sense in your head. The reason they specify V with a subscript of W is because this is the velocity of a large object, whereas this is the velocity of a wave. So let's take a look at how to solve these type of problems. A wave on a rope has a wavelength of 2.0 meters. Okay, so 2.0 meters is the wavelength. If you don't like to draw this symbol, write a W. And a frequency of 2 hertz, the letter F. What is the speed or velocity of the wave? So the formula with velocity, frequency, and wavelength is V equals F lambda. Notice frequency and wavelength are being multiplied. Therefore, they go in the bottom, side by side, multiplied. Then velocity goes on the top. Now, since we're solving for velocity, we cover up velocity, and it's frequency times wavelength. That's the only thing you have to show. 2 times 2. 2 meters times 2 hertz. And when you're done, you'll get 4 as your answer. Now, what unit do we use? Well, it's velocity, and velocity must be in meters per second. Let's review the symbols and the units for each of these things. Velocity has to be in meters per second. Frequency has to be in waves, understood 1 wave per second. And wavelength is going to be in meters. You try number 2. It's pretty similar to number 1. Now let's talk about some things that happen to waves. The first one is reflection. A wave is reflected when it bounces off a surface that it cannot pass through. It does not change the speed, the frequency, or anything else of the wave. It just flips it upside down. For example, when you look in a mirror and you have a word written on your shirt, that word will be written backwards in the mirror because it flips the image as it's reflected back to your eyes. If you've ever seen an ambulance, on the front of the ambulance, the word ambulance is written backwards. Why would they do that? Well, that way, if you're driving a car and you look in the rear view mirror, you'll actually see the word ambulance written forwards in your mirror. As another example, notice how I've sent the wave upwards and it's reflected downwards. Also, if I send the wave to the right, it's reflected to the left. Refraction occurs when a wave bends as it enters a new medium at an angle. It must enter at an angle or you will not see the refraction. It does this because one side of the wave moves more slowly than the other side. Let me show you some examples. Here's a picture from your Prentice Hall Physical Science textbook. As you see, this lawnmower is rolling from the grass onto some gravel. At an angle, notice it's not going straight onto the gravel, it is going onto the gravel at an angle. When the right-hand wheel touches the gravel, it slows down because it's harder to push the lawnmower through the gravel. But the left-hand wheel continues to move more quickly because it's still on the grass where it pushes more easily. Once that left-hand wheel touches the gravel, it slows down too, and then the lawnmower straightens out once it's completely in the gravel. So you'll notice that the right-hand side of the lawnmower slows down before the left-hand side does as it enters the new medium, the new material. Therefore, the path of the lawnmower bends as it hits the new medium. That's like a wave. When a wave comes in at an angle into a new medium, it will move faster or slower in the new medium and bend. That bending as it hits the new medium is referred to as refraction. Here's another example of refraction that you probably have seen before. If you look right where the straw meets the water, you'll notice it looks like the straw has been cut. That's because as the light passes from the water to the air, it bends the light. Now notice that if you look straight on the straw, you don't see that refraction anymore because it's not entering the medium at an angle. It's straight ahead. But now that it's entering towards the side, you can see where it looks like the straw is cut as it goes into the water. The next thing that can happen to a wave is diffraction. This is when a wave bends as it either moves around an obstacle or passes through a narrow opening. Let's take a look at an example. Let's take a look at this ripple tank. Okay, it's a tray filled with water. But if I cause a wave to pass through this small opening, do you see how the wave spreads out as it passes through? That's diffraction. The wave bends and spreads out as it passes through a narrow opening. Diffraction also occurs when a wave passes around an object. If you'll notice, see how the wave kind of bends back together on the other side of the object? That's another type of diffraction. In fact, this is how the Hawaiians and the Polynesians could tell that there was an island far, far across the ocean where they couldn't even see it. They would watch the way the waves came into their island and would say, aha, there must be something else further out in the water. Waves are also affected by interference, which is when two or more waves overlap and combine together. There are two types of interference, constructive and destructive. When you construct a building, you build it. So when two waves combine constructively, they add together. For example, if two waves pass each other and their crests line up together and their troughs line up together, these two waves will combine to make an extra tall and extra deep wave. Destructive interference destroys the waves. They cancel each other out. For example, when a crest and a trough or a trough and a crest mix together, these two waves will cancel each other out completely. These two waves will cancel each other out partially. This trough is bigger than this crest, so a smaller trough will be left. This crest is bigger than this trough, so a smaller crest will be left. Next, a standing wave is a wave that appears to stay in one place. It does not seem to move through the medium, even though it does. On that standing wave, you will find nodes where the wave appears to stay still, and antinodes where the wave appears to have a crest, a trough, or both. This is a standing wave. See how it looks like it's just kind of hovering in space? That's when there's destructive interference at the node, which is that point in the middle where it looks like it's going nowhere. And then there's constructive interference at the two antinodes, the place where there's a crest and a trough. And that's what a standing wave is. Musical instruments use standing waves. When a guitar string is plucked, the string vibrates at a certain frequency and causes a certain sound. If you take a guitar string and pluck it directly in the center, you can get two waves to occur and the sound is higher. If you could reach out and pinch this node and hold it still, the wave would continue to travel through the string even though you were holding on to the node. Isn't that cool? There we go. This has two nodes. Can't keep that up long, but that wave had two nodes and three antinodes. It was 1.5 wavelengths long, because remember, one wave has both a crest and a trough. So this was a crest, a trough, and a crest, meaning 1.5 waves. Resonance occurs when constructive interference occurs over and over inside a wave, and it vibrates until the entire object is vibrating along with that wave. That's called resonance. Musical instruments exhibit resonance. For example, a didgeridoo is a musical instrument that uses resonance. What I did, I vibrated my lips and vibrated the air inside of the tube so that the air, the entire tube, shook with the air. That's called resonance. I set up a standing wave of just the right frequency inside this tube. The modern Aborigines of Australia teach their children to play a didgeridoo by using PVC pipe. It's a whole lot cheaper than a real didgeridoo. It's kind of like your parents buying you a cheap guitar to find out if you're actually going to play it before they buy you a more expensive one. Low sounds have a long wavelength, a low frequency, and a low pitch. High sounds have a short wavelength, a high frequency, and a high pitch. But what does that mean? The longer the didgeridoo, the longer the wavelength of the waves inside. Notice the lower sound. See, when a wave has a long wavelength, it has a low frequency. The waves don't come by very frequently when there is a long distance between two crests or two troughs. When a wave has a short wavelength, the waves come by much more frequently. So, wait. See, high frequency, short wavelength. The energy of a wave is also related to its wavelength and frequency. This long wavelength, low frequency wave has a low energy. This high wavelength, high frequency wave has a high energy. So when wavelength increases, frequency decreases. And when wavelength decreases, frequency increases. It's an inverse relationship. When one goes up, the other goes down. What if we have a really long didgeridoo? You see how low that sound is? That's because that really long wavelength inside the didgeridoo creates a very low pitch, while a shorter didgeridoo produces a higher pitch. What happens if we use a thinner didgeridoo? Do you think that would be a higher or a lower pitch? Let's find out. Let's compare it to this one since they're about the same length. See how the wider one has a much lower pitch and the narrow one has a higher pitch. By the way, if you want to learn how to do this at home, here's how to play a didgeridoo. First you have to do this. Okay? But you have to make this part of your mouth hold still, and only the middle of your lips can flap. Okay? Not. That's correct. So then, see, you'll mess up. Then adjust and try going faster and slower. Like that. Until you get a frequency that resonates with the air in the didgeridoo. There we go. See, I tried different rates of lip flapping, different frequencies, and that finally gave me the correct frequency to resonate with this instrument. In order to play the shorter didgeridoo, I have to do this. In order to play the longer didgeridoo, I have to do this. See how that's slower, less frequent? Here's another example of resonance. Get a stemmed glass and put some water in it. Hold the base of the glass so you don't knock it over. Dip your finger in, and then run it around the edges of the glass. Isn't that cool? Now, if you could sing that exact note, you could actually break the glass. If you look at the glass from above, you can actually see the vibration of the water as it vibrates and resonates with the glass. Notice the lower pitch when I filled the glass up more, and the higher pitch when I filled the glass with less water. This was how Sandra Bullock played her talent in Miss Congeniality 2. So the official definition of resonance is it's the response of a standing wave to another wave of the same frequency. If the waves are timed correctly, the waves add together to higher and higher amplitude. You heard once the air inside that didgeridoo started vibrating, the entire didgeridoo vibrated at that same frequency, magnifying the amplitude of the waves until it just rang with a sound like a horn. Another example of resonance is the body of a guitar. When you pluck the string, the hollow body, the air inside the body of the guitar will shake at just the right frequency. It will resonate, and that will make the guitar louder. A bridge can actually undergo resonance if the wind blows or if soldiers march across it. When soldiers march across a bridge in unison, they actually get it to bounce along with their walk, and it can actually jolt the bridge so badly that it actually collapses the bridge. So soldiers will actually break cadence when they walk across the bridge and will not walk across in unison. A famous bridge in the state of Washington, the Tacoma Narrows Suspension Bridge, actually collapsed because of resonance with the wind. This bridge was nicknamed Galloping Gertie because it actually just truly galloped when the wind got up. And one day in 1940, the wind matched the frequency of the bridge, and there were such high winds that the entire bridge collapsed. The video is next on Canvas. Make sure you watch that. The Doppler effect is a change in frequency caused by the motion of the sound source, the motion of the listener, or both. An example of this is a change in pitch of a siren as an ambulance passes you. Have you ever noticed when an ambulance goes by or a car goes by blowing the horn, it goes, that's the Doppler effect. Have you seen the episode of The Big Bang Theory where Sheldon dresses as the Doppler effect? Personally, I think he looks a little bit like Beetlejuice. He's wearing a black and white striped outfit. The stripes are narrow and then wider and then narrow. And what he's trying to show is the bunching together of the waves. Let me show you using the wave pool. Here's how the Doppler effect works. If I have something producing a sound, the waves go out in concentric circles. The sound is heard equally from any place around it. But if the sound source moves, notice how it's bunching up its own waves in front of it and is stretching out its own waves behind it. When the waves bunch up more closely, you hear a higher pitch. When the waves stretch out behind you, you hear a lower pitch. So when a car goes by blowing its horn, you hear meow. That's because the sound waves are bunched up in front of the car as it comes towards you, and the waves are stretched out as the car moves away from you. Sonar is sound navigation and ranging. This uses ultrasound, a higher frequency than we can actually hear, to determine the distance to an object underwater. So let's say that this is the water. You're in the boat up here, and you want to know what the bottom of the seafloor looks like. So the sonar sends that sound, and it takes this long to get back. All right, this amount of time to hit the bottom of the ocean floor and come back to your detector. And it will tell, by the time it takes, it will tell how deep it is. Then it goes here, this is shallower, so the waves return faster. So they know it's shallower here. Then here, the waves take a longer time to return, they know it's deeper. And so that's how they tell the depth of the ocean floor, and they tell how the ocean floor goes up and down underneath. Radar works in a similar way to determine how fast a vehicle is moving. For example, if you are moving towards a police car who has their radar on, then you will be bunching the waves up and pushing them more quickly towards the radar. If you are moving away, it'll be stretching out the waves. That radar can detect how much the waves are compressed or stretched out and determine your speed. Pretty much any sound you make will use standing waves or resonance. For example, you've probably made a piece of grass or a piece of paper squeak. What this does, it causes the paper to vibrate and resonate until the sound gets louder. Have you ever made a farting noise under your armpit? Once again, that's resonance. Have you ever made that sound like a train with your hands? That's resonance as well. The air is resonating in the pocket inside your hands.